Interventional radiology has been developed from catheter-based diagnostic angiography. The first steps in the direction of therapeutic angiography were made in the early 1960s. Andreas Grünzig developed a dilatable balloon catheter, which he used for the first time on a patient on September 16, 1977, with immediate relief of symptoms. This procedure established Grünzig as a pioneer of interventional cardiology. The intervening years have witnessed the continuously rapid development of new techniques and applications for interventional radiology and cardiology. This period has also seen significant improvements in radiation protection for patients and medical personnel during examinations.
There
are strict requirements for technical equipment and specific application-oriented staff training based on strict attention to radiation hygiene principles. Interventional procedures require more time, with the result that radiation exposure for physicians and patients is significantly higher than in straightforward diagnostic examinations. The treatment rooms comply with the requirements for constructional radiation protection, as stipulated in the X-ray Ordinance. Appropriate protection must be provided for patients and attending medical personnel. These control zones, as they're called, are clearly labeled with the radiation symbol. All X-ray equipment requires operating approval from the appropriate authorities. The operating manual is the reference for information on how to correctly use the X-ray system. Detailed information on radiation protection, particularly scattered radiation exposure in specific work areas, can be obtained from the clinic's radiation protection expert. To prevent long-term damage, the procedures described, as well as the manufacturer's instructions, must be followed carefully. The rate at which X-rays penetrate human tissue and produce the X-ray images is dependent on the X-ray type and quality. Useful beam is the term that describes this concept. Part of the X-ray beam is deflected in the tissue and randomly scattered in all directions. This is known as scattered radiation and is one of the causes of radiation exposure in attending medical personnel. To minimize such radiation exposure, it's vital that the personnel observe the safety measures shown here. The following instructions should be followed for the highest level of protection against unnecessary radiation exposure. Adequate preparation is required before each intervention with the X-ray system to ensure correct patient positioning and procedural planning. The X-ray system should be positioned as optimally as possible. It is important to check that the equipment to protect the patient is used properly. Sufficient protective equipment should be available. Isodose curves illustrate the scattered radiation intensity in typical regions of interest, depending on the examination type and technique. Identical colors represent zones with identical radiation intensity. Scattered radiation exposure in attending medical personnel is directly linked to the distance from the radiation source. Scattered radiation exposure is significant in the red area. The scattered radiation intensity diagram shown here is obtained in the lateral view. In the case of lateral examinations, the X-rayed volumes are larger, with the result that the scattered radiation intensity is higher. In radiographic series, the scattered radiation intensity is significantly higher than with fluoroscopy. Radiation exposure in attending medical personnel is recorded during examinations by various dosimeters. These dosimeters are regularly evaluated by the dosimetry service. The following points must be observed when wearing dosimeters. The whole body dosimeter is worn on the torso at chest level, or in the case of pregnant women at stomach level, under protective clothing. A second dosimeter should be worn over protective clothing in high-dose situations, such as interventional examinations. These devices must be appropriately labeled to avoid confusion during evaluation. Hands are often exposed to elevated levels of radiation during interventional examinations. For this reason, a ring dosimeter should be worn in addition to whole-body dosimeters. The clinic's radiation protection expert can provide information on how to minimize local doses and on how to wear the dosimeter. Operating staff can receive effective protection against unnecessary radiation exposure by following a set of important rules when in contact with X-ray systems. Protective clothing must be worn in control zones by staff exposed to radiation at work. The user must wear lead glasses and shields to protect the thyroid gland and sternum. If used properly, these measures will provide effective protection against radiation exposure. It should be remembered that protective clothing only fulfills its purpose if worn and stored correctly. All protective equipment has to be checked regularly to ensure it is operational and effective. Protective equipment at the examination table helps significantly to reduce radiation exposure for attending medical personnel. The following protective equipment can be used during examinations: a pivoting protective shield attached to a ceiling support, a radiation shield at the catheterization table, and a mobile radio protective screen. The positive effect of the protective equipment on the radiation intensity applies in the basic views as well as the lateral views, in areas where the medical personnel will typically be. X-ray systems for interventional radiology and cardiology feature extensive additional technical equipment to minimize scattered radiation exposure in attending medical personnel and radiation exposure in patients. The effective positioning is shown here. The smaller the body surface area radiated, the smaller the X-rayed volume. Patient organs are thereby protected and scattered radiation is reduced. Positioning has a major impact on image quality. The devices provided by the system, such as wedges and shutters, are to be used with positioning without radiation. Additional filters primarily reduce unwanted soft X-rays that do not contribute to the image quality. Modern systems come with a range of powerful additional filters that can be programmed and operated automatically. Using these additional filters can dramatically reduce both the patient dose and the dose rate for the examiner by up to 80%. This dose-reducing technique is highly recommended, especially in pediatrics and electrophysiology. The system's optimized examination programs have to be used. Every X-ray system for interventional techniques has an automatic function for adjusting the fluoroscopic and radiographic parameters. Since these adjustments are automatic, they should always strike a perfect balance between low dose rates and high image quality. The last image hold, or LIH function, enables the examiner to evaluate a frozen fluoroscopic image. This feature means the exposure time can be reduced. Modern systems support functions for storing fluoroscopic sequences. Thanks to this technique, fewer radiographic series are needed, leading to further reductions of scattered radiation exposure in attending medical personnel and radiation exposure in patients. The significantly improved image quality offered by pulsed fluoroscopy enables the examiner to reduce the overall fluoroscopy time and thereby decreases the patient dose. Pulse rate, intensity of exposure, and pulse duration have a direct effect on the dose rate in patients and users. Radiation exposure can be reduced by choosing the best examination parameters for fluoroscopy and radiographic series. In the road mapping technique, the last image hold X-ray is used as a mask during the first fluoroscopic cycle with contrast injection. Vessels filled with contrast agent appear dark. Before the next fluoroscopic cycle, this mask is removed from the actual X-ray image so that the guide wire or the catheter can be visualized and tracked. Road mapping helps the examiner to work more efficiently and, above all, to minimize doses of radiation. Patients and attending medical personnel now receive optimum protection during examinations. Thanks to the implementation of international standards, the introduction of suitable national diagnostic reference values, and the ongoing efforts of system manufacturers, radiation protection is increasing steadily for patients and medical personnel during examinations. Modern systems record, calculate, and store various dose values in addition to the dose area product. These values are displayed on the monitors in the control room and examination room. For physicians, information is therefore available at a glance on both current and cumulative skin dose and dose area product values. A dose report can be printed out after an examination and archived in the patient's file. Diagnostic reference values, known as DRVs, enable ionized radiation users to estimate radiation exposure in patients. These values do not represent limits, but rather set the permitted range for normal exposure. The dose area product is used as a representative dose value in fluoroscopy-based applications. As the name suggests, the dose area product is made up of the dose and the radiated area, and represents a value for the patient dose. Diagnostic reference values are set by the authorities in compliance with national and international recommendations. If the DRV is regularly exceeded in examinations conducted under normal conditions, the system will suggest optimization processes or practice changes. Planning the examination, selecting the optimum fluoroscopic and radiographic parameters, and selecting the optimum image detector format and wedge shutter. Here is a summary of recommendations. The scattered radiation intensity must be kept in mind during an examination. It is necessary to keep as much as possible to low exposure green zones. One dosimeter is worn under protective clothing for high dose examinations. Another one is worn over the protective clothing. A ring dosimeter also is worn. Personal protective equipment is always used, and used as shown. The radioprotective equipment available in the area of application is beneficial. All the technical protective possibilities that the system offers are applied, such as additional filters, last image hold, radiation-free positioning of wedges and shutters, pulsed fluoroscopy, and road mapping. Advanced team planning on how best to implement the radioprotective measures shown here is essential. An additional measure of great importance are the diagnostic reference values published by the authorities.